This is 9.2.2, user input threats. So at the end of this lesson, we should be able to answer the guiding question down here. How do malicious actors exploit vulnerabilities in areas of a web page that's designed for user input? And what can we do to mitigate those risks? So most programmers are focused on making their applications actually work, and also meeting their deadlines to publish their code. That means usually security is overlooked or often not considered a priority during the coding process. But as we're going to see in the next couple of slides, that practice is very short-sighted. So the following slides, we're going to discuss each of these types of code-based vulnerabilities except for SQL injection, which is covered by itself in the next lesson. So the common thread between all of these is that the code is interactive, and it's the user input that offers the adversary an attack opportunity. Directory traversal attacks are pretty old school. There should be many layers in place on a website to avoid this type of attack, but this concept can also be integrated into other methods of intrusion, so it's really important to understand this concept and its execution. So understanding directory traversal is essentially about understanding file system structure. So remember the command cd. That's going to move us from the current folder to its parent folder, aka cd is going to move the path up one folder. So we can use this command right here, the .. to achieve the same movement. And then in Linux, we know that it's just a / that's the very top directory or the root. In the image, you can see that in order to move from Bob all the way up to the root folder, we could type cd 3 times, or we can type it this way. So let's look at this example. We're going to use this command to move up 3 folders. So we're starting here. The server has a URL that points to access files like this right here. If the server accepts user changes to the URL, then the attacker could add text to the URL like below to traverse up to the root and then access another folder and file. So the attacker would add this to the URL, which would cause the server to process this. And believe it or not, granted, the password file doesn't hold actual passwords, but it would give us the list of users. And it is possible that it would also work to read the shadow file if our changed URL is accepted as a system request. Buffer overflows insert code into the memory buffer of a process where the data is actually larger than the input variable can hold, and the process overflows into process execution space to run its hostile code. Buffer overflows are a common result of the mismanagement of memory on the part of app developers who might not be educated in these security risks. So in essence, if a hacker provides too much data in exactly the right spot in the code, it becomes possible for that data to be processed as if it was application code instead of just user input. So in the example I'm about to demonstrate with an animation, our programmer is assuming that all of the names provided by the user will be a maximum of 5 characters. So 5 spots have been allocated in the buffer storage, and we can see that here. So when our hacker Iron Man comes along, his name is actually going to fill up all 5 spots in the buffer storage and then flow over into the next part of the storage. So if that part of code storage includes executable code that is expected to be processed, then any code the hacker attaches to his name input will also be processed. Command injections insert text into form fields that are passed into an executable process. So the goal here is usually to run terminal commands on the hosting server. A command injection vulnerability exists when a website takes user input and runs it using operating system processes. This means that an attacker can provide commands in the input field, and the website will run the commands as if they were in the terminal. And the key to making the website think that there are two pieces of information to collect and process. The first is the answer to the website's form question. So let's look at this example. We are trying to fool the website into accepting multiple commands by using special characters like the semicolon or a backslash. The question is enter your name. That's what the form wants us to do. So we provide Joe Schmo. And then this is going to be added to a database or a list as per the website process code. So inserting a special character like this semicolon or this backslash is basically interpreted in code as, hey, here's another command. We use the semicolon a lot in code. There are a ton of other characters that can achieve the same thing. Try Googling command injection cheat sheet. Maybe I should print off a copy of that. Anyway, the second key to making the website think that there are two pieces of information to collect and process is the actual command that is injected. Cross-site scripting. This is a big deal. So there is a lot to know about cross-site scripting. It takes advantage of a basic web security concept, the same origin policy. So that basically says if content comes from one site like Amazon.com, and I've already granted Amazon permission to access the resources on my PC, then any content from that site is going to share these permissions. That's not good, usually. So cross-site scripting is defined as a malicious actor who adds script code into a user input field on the website, which is later executed in a visitor's browser, also known as the client side. So this is how cross-site scripting works. First, cybercriminals exploit the cross-site scripting vulnerability by injecting scripts that contain malicious code into a web page. Second, the web page is accessed by the victim, and the malicious scripts unknowingly pass to their browser. Next, the malicious script can access any cookies, session tokens, or other sensitive information about the user, which is sent back to the cybercriminal. And then finally, armed with this information, the cybercriminal can impersonate the user. So cross-site scripting attacks are prevalent across the internet, but in most cases, the victim is never going to know that anything happened because there doesn't have to be any visible action. Cross-site scripting can be implemented so the victim doesn't even need to click on anything for it to work. It's just there. All they have to do is visit the affected website. This is also known as a drive-by. So an attacker can use cross-site scripting to send a malicious script to an unsuspecting user. The end user's browser has no way to know that the script should not be trusted, and it's going to execute the script. That's another way of saying it's going to run the script. So because it thinks the script came from a trusted source, the malicious script can access any cookies, session tokens, or other sensitive information that's been retained by that browser and used with that site. These scripts can even rewrite the content of the HTML page, which is pretty insane. Cross-site scripting can be used with almost any type of web interface or application. You can find it on discussion forums, forms that you fill out all over social media websites. So I have a stored cross-site scripting scenario for you. Try to follow along here. But let's say that there's a website that allows users to post or search for cars for sale. So we have Bob. Bob is an authenticated user, meaning he has a cookie. Bob has a cookie. And Bob posts an ad for his car and includes some special HTML to make part of the ad text show up as bold. Alice is also an authenticated user, so Alice also has a cookie. And Alice likes to regularly look on this website for cars. So enter Mel. Mel is the bad guy. And Mel likes to use cross-site scripting attacks. That's his style. So he notices that Bob's ad uses special HTML, and he knows that because the text is bold. And HTML is how you would code that on a website. So that tips Mel off and indicates to him that the website might take any sort of code, including JavaScript. So Mel creates his own car for sale post, but he includes a script that's going to try to steal someone's cookie when they read his ad. So when Mel publishes his ad, it does not check to see if there's any suspicious code, so it misses the JavaScript. Alice goes back to the website again to look for cars, and she clicks to read Mel's ad. So the script in Mel's ad is invisible, and it grabs her cookie out of her hands and it sends it to Mel. So since this is Alice's current cookie for the website, Mel is able to use it right away to access the website as Alice. And he can view or change Alice's profile, post ads as Alice, even steal her credit card info if it's stored on the website. Input validation to secure online code. So as we've seen already, web applications have become interactive, and they often have features that accept input from users. Usually that's in a form field of some sort, but that user input can be the perfect opportunity for a hacker to insert malformed data. And that is why validating the input is one of the most important methods of defensive programming. Defensive programming being programming with security in mind. So validating input could mean making sure that a password field doesn't accept more than 15 characters, as it would be possible to pass a script code into a larger field, or the program might need to validate the input as being an integer before it's passed into the executable code, because if the user provides a fraction, it would crash the code. Then we have escaping characters. The effort here is made to disable the effectiveness of certain characters as executable code. So examples are some of these characters right here. Basically, the websites are configured to replace those special characters because these are often used in scripts. Allow listing is a very sensible reaction to the fact that we cannot predict what a user will do. However, when the possible acceptable answers to a question can be listed, it makes sense to limit the user to just those answers. Addresses are the perfect field to allow list because it is possible to load a list of states or countries or zip codes. Or even better, don't let the user type anything in at all. Provide some sort of drop-down list of the acceptable choices, and you take out all of the risk of script injection.